Welcome everybody to the second installment of the webinar series, Engineering a Touring Tiny House. So this week we're talking about insulation, air sealing, and weather barriers. Everybody might be like, why are we talking about this stuff? And it's because this is all way, way more interesting than you would think if you didn't know about this. So if you're a tiny house person, if you're a regular home person who likes the idea of tiny houses, if you're just a regular Joe, if you are a building scientist like we are, you're going to get something out of this. So I hope that you all enjoy this. As we go, please type your questions into your questions pane. This is very important because, number one, we don't want you to forget your questions. And number two, when we get to the end, we're going to slam open that questions pane and start answering questions like crazy. And if there are not a bunch of questions already waiting, then it slows down a lot. So I would rather be able to just take a running leap at this stuff. And running leap is how we generally are going to do all of this. So you've been seeing a static screen for a few minutes, and we're going to make that go away.
And one other thing I wanted to say about why insulation, air sealing, and weather barriers are exciting. I often translate Corbett's geek out on the science world. What these three things mean at the end of the day is they mean comfort. And you can ask anybody. They want to be comfortable in their home. So yeah. Let's go.
So why we are talking about tiny house at all, why we're engineering this high performance and performance proven tiny house is the Proof is Possible tour. This is a 16-city U.S. tour that we are going to execute in 2016. And when I say execute, I mean it in the most exciting way. You can see the mind map of this tour over here on your left. All the things on the right of this mind map are chronological as we arrive in a city, and all the things on the left are the assets and the things we're doing while we're there, which is kind of, it's crazy. If we were to go through all of the things that we're doing on this tour, it sounds insane. So we're not going to go through all of that. The main thing that you need to understand is that we're going to be using this tiny lab to train consumers, to empower them to understand measured home performance. Measured home performance does not mean energy efficiency. If you need more background on that, feel free to watch the first video in this series, which was all about the shape and the layout. And we're going to go through all the rest of this stuff. We're going to get deeper and deeper into the performance aspect of things as we go throughout this series. So I hope you'll continue to tune in. So while we're on the road, we will also be making the Home Diagnosis TV show. This is going to be made, number one, we are committing to it because we are not like a giant corporation. We're a tiny company, and we do whatever we want all the time. Grace is a film producer, and I spend a lot of the time in front of the camera and doing these diagnostics. So we are not joking around. We're not trying to raise money for this at this point. We're doing it, and people can come and participate with us, which we would love so much. But if they don't, we don't care, because we're going to do it anyway. So please do consider being either a fan of the show when it starts happening, or being a supporter in making it happen. And as we go throughout our 16 cities, we're going to need places to solve building mysteries.
Yeah, so if you have a really complicated house in Oakland,
we are your friends. Yeah. We can help you. Okay, so real quick, I have a 5-minute video on this that you can check out. And also, it's explained in the handout, which you can find in this webinar. If you were in the webinar, you get the handout. If you're watching this on a video, you don't get the handout. So you need to visit our website to get that. But in the meantime, you guys should be looking at this. This explains it a little bit more in depth. But in general, what you need to understand is that home performance is made of a 4-3-2-1 kind of framework, the way that I teach it. So there are 4 elements to home performance. There is heat, there's pressure and airflow, there's moisture, and there's IAQ, which stands for indoor air quality. That list is in increasing order of importance. Indoor air quality is the single most important thing on the list. Everybody needs to be healthy and happy and not smell bad things in the house, because those are the main problems that most companies are getting called about. And then moisture is going to tear apart the house. We've got pressure problems and heat flow problems that people aren't even aware that are happening in the house. There are 3 improvements on any building plan or home improvement process. And that means, number 1, air sealing, which you might not even know what that is. Number 2, insulating. And number 3, and lastly, HVAC. Most people think, oh, I should get a new air conditioner, or I should get a new furnace, or I should get my ducts cleaned. That's HVAC stuff. That's all at the end of the list. If you're not hitting the first 2 things, it's not going to work. We'll go through that today. The 2 systems in any home that have a major effect on the home performance are the enclosure, which we're going to talk about a lot today. That's the air sealing and insulation and weather barriers. That's all the stuff that we're going over. And the engines. The engines are what we're talking about next week. That's anything that moves air or heat within the house or between the house and outside. And that includes water heating and things like that. There is only one goal of all of this, and that is control. It is not energy efficiency. It is not sustainability. It is not all of the wonderful things that we all probably believe in on this webinar. And that's fine, because all of those things are side effects of having control over your environment. And control doesn't mean iron fist. It means knowing what's about to happen before it happens, and not wasting a bunch of money trying to solve problems that you don't actually understand.
So when we originally started doing building science here in Chicago, our company was called Green Dream Group, which you can still find. And one of the green dreams that we love is that you don't have to think about any of those other things, of sustainability, efficiency, etc., if you do get to that one goal of control. So side effects, byproducts, happy accidents, green dreams, that's where it goes to.
Exactly. Now, ultimately, the only way you can prove that you have control over your home is performance testing. That is the end of the line. So that is what we teach. That is what I specialize in. That's what we're going to be making the television show about. Performance testing is the essence of everything we're talking about, not just the building science. Now, here is how to build anything in the world, but specifically we're talking about the tiny lab right now. Number one, you design what it is you are about to do. You lay out the steps, the order of things you're going to use, the inventory of materials, etc. Then you start actually putting it together, and you install all the things together in a quality way, and then you check to make sure that all the stuff actually happened the right way, right? When you're, this laptop that I'm talking to you on is the newer one. The last one that I had went bad, and we actually baked it. If you don't know what that is, it means you literally remove the logic board and you put it in the oven on 375 for like 8 minutes, and you bake the thing back together. And when you put the computer back together, you might have a screw left over. If you have a screw left over, you take that thing back apart and you figure out where that thing goes, right? You make sure to double check yourself. And with homes, you would be floored.
Amazed
at what does not get checked. Literally 0% of anything gets checked in most building construction sites. And that means that, number one, it's our fault as homeowners because we rush contractors. We're trying to tell them, I want it on my schedule, and I want it for this low price, and I don't want any guff from you, and I want it, yesterday. And I'm going to give you a bad review if you do anything, right?
And you're going to get what you pay for.
Exactly. And so we need to understand that we have trained our contractors and our building professionals into working very fast and very sloppy, and it is our fault. Number two, the contractors can start making more money because they can actually prove that they deliver quality, and that is all of the steps that we're talking about here on the left, which is not a big list. It's very, very simple to do this stuff. So, design and engineering is the thing that we're really focusing on in this webinar series. We are going to be showing you the installation and the verification. The installation is going to be in videos that are going to be made later this year. November through March, we're going to be building this tiny lab. And while we're on the road, we're going to be demonstrating the verification tools, right? So the picture that you're seeing on the left, as we're talking about design and engineering, is a LEED certified home. That is not a facetious remark. That literally is a picture from a house that I was hired to verify that everything happened as according to plan. If some engineer had built, or architect had built a plan that looked like that, they would be laughed at. However, it happens in real life all the time, and that house is going to be certified, and that is wrong. There is no reason for that to happen in a code certified home, let alone a LEED certified home. So what you need to understand is that products and labels are not going to be the heroes of the day. You could buy all the best stuff off the shelf and install it and get some label to put on your house. And if there was not design and quality installation and then verification to prove that all this stuff happened the right way, your house is not going to perform well. And I can tell you that I test equally, in equal measure, old homes and brand new homes. Everybody has problems in their homes, and it's because new does not mean better. Number two, measure twice, cut once, right? That's the adage. Please take care of me. And you want to make sure that you don't waste your time, don't waste materials, make sure that you know what's about to happen before you do it, right? Next, we remember that since we're building this tiny house, and not everybody's going to build a tiny house, this works for every house, but because we've got a tiny space, any tiny shift in it will make a huge difference because there is no wiggle room in this house, especially with what I'm about to show you that we're going to build into this thing. Now, there's a thing called the 1-10-100 rule. this means that those 3 steps that I just showed you, design, installation, and then verification, means that I could spend $1 today designing something in the right way. But if I was to wait until I actually install it wrong, to do a change order on that item that I just did wrong would cost 10 times as much as it would have cost in the design phase. And if I was to install the thing and then wait until the very end and have something go wrong with the house, it will cost me 100 times as much as it would have cost for me to fix the problem in the design phase. This is critical for you to understand because you will spend more money on a better quality product, period, right? We all understand that. But you will not have the problems down the road that are, what is this called? Exponentially, right?
Yes.
Exponentially more expensive than it would cost you upfront to do it the right way. So that's something that's critical to just understand. Now, just to review, here's the layout of our tiny house. Again, this is called a tiny lab. It's got an underloft instead of an overloft. It has the bathroom at the front along with the kitchen. That means the plumbing is really short. We're going to talk about that in 2 weeks when we talk about the bells and whistles. It's got the little dining booth, which I'm really excited about, etc., etc. Okay, so the 2 systems that we're talking about, remember, were the enclosure and the engines. The enclosure is your barrier. And this is for any house, not just a tiny house. This is for any single house. It is a barrier against air leakage, number 1. And air leakage is the most important and most misunderstood problem in most homes, period. Number 2 is heat bleed, and that's because of insulation issues. And number 3 is liquid water, right? So we want to block these 3 things from happening. We don't want liquid water inside, obviously. Now, here is the secret to how to plan for it. You need to understand the basics. Number 1 is the more corners you have in your house, the more problems you will have, period. And that is because corners are the enemy of both air leakage, the enemy of air sealing. It's very hard to make 2 things that come together work really well to become one thing that's seamless. We call it monolithic. Sounds very exciting, right? So the more materials you have coming together at corners, the more difficult it is. Second thing is that the devil is always in the details in architectural practices. And that means that you need to ask every single time somebody says, oh, we're going to do the roof like this. You ask, how exactly are we going to do this? And they say, well, we're going to do exactly like this. And then you say, okay, so that little thing that you just mentioned inside of what you just said, how exactly are you going to do that? And drilling down to the details is my job. That is what we get paid for at Building Performance Workshop by architects and developers of huge buildings. My job is to look at building plans and say, this seems a little vague. How exactly are we going to do this? And we get down to the nitty-gritty and find out exactly how everything is going to work out perfectly. Now, the next thing is you need to be able to trace the barriers. Trace the liquid water barrier, the air sealing barrier, and the heat bleed barrier with a pencil and not have to lift it. And here is how this works. You can see on this plan on the left, I draw a red line. And then I have to lift my pencil because you see that there's that little corner. And I can draw the wall and the ceiling, and then I have to lift my pencil again. So these 2 areas right here are going to be my problem spots. And I can see that coming from years away. So what I can do is either fix that or install some kind of a monitoring measure so that I can either install a little sensor or install a hatchway so that I can get to that spot. Because if there are ever going to be problems in this house, those are where the problems are going to develop.
One other way to think about this, the devil in the details, right? We all have to sit down at some point in our life and go through a contract with a lawyer, right? And they are there to specify the devil in the details because they don't want you to have to pay for it later and get in trouble down the road. And this is exactly the same thing.
So this is exactly how this works out. You need to design the details into your plan or your contract, like Grace was mentioning, for air sealing. And that takes care of the air leakage barrier. For insulation, that takes care of the heat bleed barrier. And for flashing, and that takes care of the liquid water. Part of what we talked about with flashing was last week on the shape and the layout. But you need to know, in all of these cases, what quality goal you are shooting for. The definition of quality is achieving a certain standard. So you need to know exactly what goal you will have hit when you say, yes, we achieved the quality that I was looking for. You can't have everything top quality all the time. You don't need it. In fact, that's one of the big things that we always are drilling into our projects is that we don't need everything to be passive house levels. And if you don't know what that is, we're going to talk about it today. But you don't need everything to be super high performance. You need to be enough performance to give you what you need, and for that you need to know what your goals are. So here's how you prove that the targets of quality are met. You use the performance testing. You knew I was going to say this, right? So here are pictures along the bottom of all of our students that have come through the Building Performance Workshop. That's not all of them, but we teach blower door testing, and we do this all the time. I recently did 18 blower door tests in a row in the last couple weeks, and that is for proving the air leakage doesn't exceed some certain target, right? And we're going to talk about that. Infrared thermal photos. This is really useful for identifying heat bleed. And using the infrared camera, again, this is part of the reason why this is a sexy tool. And you can see lots of videos of us using it on our video channel for liquid water. Now, the first target that we're going to talk about is air sealing, right? So for the Tiny Lab, what we are aiming for is 2 air changes per hour maximum. And I'm going to explain all of this stuff. If you're not getting the lingo, don't worry about it. Grace and I are going to break it down for you. Grace obviously is the translator on this stuff. But we're aiming for 2. That's the number you need to remember right now. The material we are using for air sealing is probably something that a lot of you haven't heard of. It's called Knauf EcoSeal. Knauf is the installation company, and we have a long working history with them. I'm not being paid to endorse their product right now. It's awesome because it's a sprayed gasket. It's what's in the picture over here on the left. So you spray where the seams are. A lot of people use spray foam, which we're going to talk about in a few minutes, and some of the things that we'll talk about will surprise you, but a lot of people use spray foam to air seal. The problem is that the plywood that you're seeing behind this gentleman, who looks very heroic in this picture, is an air sealing material, except where the seams are. So this is very material effective, very cost effective, and no VOCs is important for 2 big reasons. The most important one is not what you would think of. What you would think of probably is that, oh, it doesn't have any of those toxic gases that I'm going to breathe in. That is nice, and I do think that that's a big deal, especially in a tiny house. But the most important thing that I care about as a building doctor is that if it's not off-gassing, that means that the material is literally not changing its chemistry. So in 30 years, this material that I sprayed on is going to be exactly the same as the day that I installed it. That is a game changer. So to me, whether or not I breathe it, and I'm going to take measures to make sure that we do not breathe it, aside from the fact that it's no VOC, we should not be breathing this stuff regardless, it doesn't matter. And we're going to get the proof with the blower door test. And the blower door number that we're going to need to hit in order to hit this 2 air changes per hour is 67. That's an awesome number. And if you guys know about blower doors, that is, I've never seen that number before.
And Corbett, for people who don't know what a blower door is, because I see 67 and CFM 50, I'm like, well,
Bingo.
those are similar. What does that mean?
Exactly. So here's how a blower door test works. This is one of our blower doors over here on the right. We close all the house up. We open all the interior doors, so we make the house into one big room. Then we create a pressure difference of 50 pascals, which is about a 20-mile-an-hour wind on every single surface of the house. And then we know, since the fan that you see there is a $2,000 fan, it's very closely calibrated, and we know exactly how much air is moving out through it. You can't create a vacuum. So the air out equals the air in, and since we know how to measure the air out, we know how much air is coming in. That is our CFM 50 number. That stands for cubic feet per minute, which is how you measure all airflow in America, at 50 pascals, which again is that 20-mile-an-hour wind. And we convert that into this air changes per hour at 50. So the air changes per hour, I'll show you. Here's this little graph that shows lots of leakage will be more. It's like golf, right? You want less. So we're aiming for 2, which is south of 3. This is how it works, basically. So we've got all of our air changes per hour. Now, this is all codes in the entire country will incorporate this by 2017. So if you are planning to have a house built, you need to future-proof your house and make sure that it is built to one of these standards so that you don't end up selling your house in 5 or 10 years and having it being like, well, this house doesn't, it needs to be fixed up in a million different ways because it doesn't meet code. So 7 over here on the left means that if I was to run that fan for an hour, I would move enough air through the fan to replace all of the air inside the house 7 times. And ditto for the 5 and for the 3. 7 is going to be state code in every single state by 2017. 5 is the state code in Illinois right now, for the past 2 years almost. And 3 air changes per hour over on the right, that's much tighter. And that is probably as tight as it's ever going to get. So if you build a house today to 3, it probably means that you're going to have future-proofed your house, which is very nice. This is Passive House. Passive House is 0.6 air changes per hour. If I've run that fan on that house for an hour, I will not replace all of the air inside the house. I'll have 40% of it left. That's what a passive house looks like, by the way. It doesn't look radical, right? You can build any style house, passive house. And this is the most intense certification. By the way, it's not just a certification. It is now code in Belgium. Every building that is built in the country of Belgium, which is in Europe, by the way, has to achieve passive house. That is awesome. Those guys know how to do it. So, why do we care about this? First of all, do we want to breathe air coming in from wherever? Remember, look, this is a picture of our house. A huge amount of my surface area is going to be pointed at the ground, which people have been spitting on and going to the bathroom on, if we're in India, and all kinds of different stuff, right? I don't want air coming into my house through any hole, especially since there's a truck in front, and in case that thing is running because we need power off the generator, I don't want the exhaust coming in my house either, right? Secondly, do I like flushing money down the toilet? You probably get from my tone of voice that I do not like that. That is one of my pet peeves. So I don't do that. And lastly, my wife, who's sitting right beside me, if she gets uncomfortable, I get uncomfortable, right? I care intensely about her comfort, and that is why I am caring about exactly how much air leakage is happening in my house. And the last thing is code compliance. You notice that 3 was the tightest I said any state would get to on code. I don't care about code. You know why? Because code compliance means that I just built or bought a D- house. If I was in high school and I graduated with a D-, that would be a failure, essentially. Even though I didn't get an F, I suck. So I'm not interested in code compliance. People who build to code are doing the D- work. Those are the people who are the dropouts, essentially. What you want is a B or an A home when you're looking at grades. That's why we're aiming at 2, because I will make sure that this house beats every code in the country for as long as I probably can.
And Corbett speaks with some strong language sometimes, but I just want you guys to know he's super passionate about this. And also, why not? Why not be an A, right? Why do we have to go to a D-? Let's all strive for the higher
We
goal.
could all get D-s all day long. They're for sale everywhere. So what you want, if you're interested in the good stuff, and I'm assuming since you watched this, you're interested in the good stuff. So the second target we're going to hit is insulation. First of all, the target that we're aiming for is ResNet Grade 1 quality. You can find out more about that on the internet. Don't worry about it right now. It just means perfect. 100% perfect. No gaps, no compressions. As you can see on the right, the thing not to do is to compress the thing, because the main ingredient in insulation is, anyone?
Air!
It is air. It is not the material that the insulation is made out of. Next thing is we have already minimized the wood in the last webinar as far as the shape and the layout goes. And that's really important because of what we're going to show you in a second. The proof to this is an inspection. After the insulation is put in, we're going to literally look at all of it, every single square inch, and be like, is this perfect? Yes, it is. Now we can put up the sheathing that's going to go over it and cover up the insulation. And we're going to use the infrared camera. So this is what I see in my work all the time. That wood is taking the place of what would have been insulation. And in both of these cases, that's way too much wood. These things are not going to perform as well as the homeowner probably imagines that they do. And with an infrared camera, you can actually find out exactly how much wood is in your walls. It's very simple to do. In fact, you cannot hide anything in construction anymore, period. That's one of the secrets of why this stuff is taking off, and it's going to be the future of the entire construction industry.
And Corbett, why would somebody use that much wood?
Because they have not planned it. A lot of times, actually, the framing plan is not built. What we showed you last week as far as our framing plan, exactly where each and every stud is going to go, that doesn't exist for most houses. You can pay someone to do that, but they assume you don't want to pay for it. So they're not building it. So then when they get on site, they're just like, let's put some wood here and here, and then we'll just do this. And they're also nervous. The guy who's installing the wood is not an engineer, and he knows that if a house falls down, he's going to be on the hook for it. So he wants to make sure the house isn't going to fall down. They overbuild this stuff. So, insulation-wise, something you understand is that there are only 2 types. There is fibrous and there is foam. That's it. Okay, so we're going to break this down. Fibrous insulation is fiberglass and wool, which means sheep's wool or mineral wool or glass wool, all those things count. Cellulose, which is ground up newspaper, which is made from trees, right? All this stuff has fibers in it. That's what catches the air, which we already mentioned is the most important ingredient. All of that stuff is about R3.5 per inch. So if you have a 2x4 wall, let's just say for the sake of argument, it's 4 inches thick, we would have 4 times 3.5, and that would give us about R14 for a wall. That's nice. Foam can be either sprayed or rigid. Spray foam is what a lot of people are talking about as all the rage and everything. And by the way, if you want to hear something interesting, check out one of my most recent building performance podcasts about spray foam. You'll learn some stuff, and I'm going to go over some of that right now. There are 2 kinds of this foam, whether it's sprayed or rigid. There's open cell, which is ½ pound per cubic foot, or you call it ½ pound foam, or open cell. That's about the same R value as fibrous. And then there's closed cell, and that's also called 2 pound, and that is about twice the R value per inch as fibrous or as open cell. Now, everybody always says, oh, well, I want spray foam, obviously, since that's the best thing, right? And the answer is no, it is not the best. Please tell your friends. This is total misinformation. There are marketing campaigns that are going on for everything. Right now, I am marketing to you for the ideas that I want you to think about, right? We're all marketing to each other, so I want you to really make sure that you're using a critical eye on all the stuff that you see about anything in building. And if it doesn't jive with this home as a system way of thinking, then it's probably not true. So all foam contains petrochemicals, and that includes biofoam. If you hear something called it's soy-based or whatever, it all has this chemical in it, period. So that means that, number one, it does have some level of toxicity that needs to be off-gassing. Number two, because I already mentioned, if it off-gasses, it actually changes the quality, the chemistry of the structural material over time. Now, second thing is that this is a chemistry experiment every single time. And if you have ever met an insulator, it's very rare that you'll meet somebody who is smart enough and applies themselves to the job enough that you think, oh yeah, you're obviously a chemist, right? This stuff is hard. And the guys who install this often are not trained very well. And I know because I know a lot of them, and they're very nice guys, but they are not equipped with the training and the kind of licensing that we would assume that they are. So there are very high quality spray foam installers out there
who are very smart.
And you need to find them and pay them better than you were planning to pay the cheap guy, because the cheap guy is not who you want. So you need to find the smart people who actually understand the chemistry experiment if you are going to do this. Because if you don't get the benefit, you just paid twice as much, even for open cell foam. That's twice as much as people would pay for a fibrous insulation. So this is something that you really need to think about and consider carefully. Now, what could go wrong? If anyone would like to guess what is in the walls of this house that I was hired to find out what is wrong with, you may do so. What I will tell you right now is that I can save you the trouble of doing all the research. That, what you're looking at, is injected spray foam. That is what I would consider to be a total ripoff. So again, the product is not going to save you. This is a house that somebody paid tens of thousands of dollars to have injected with spray foam between the brick and the plaster walls, and it did approximately nothing. And that's because I'm going to show you some math in a moment. By the way, here is a picture on the left of all kinds of different insulation installed badly. There is a picture of spray foam without the stuff that's covering it up that would look like, with an infrared camera, what you saw just a minute ago. And on the right is a picture of someone's crawl space in $1 million house. And I do a lot of $1 million houses, and I know that in these cavities where people don't think you're going to go and take a look, they leave a total mess. And that includes the inside of your walls. That's why you ask someone to prove that they gave you what you paid for. And that's why you also pay that person more, because they are doing the job the right way. So these two things are really, really hand in hand. You need somebody to prove it to you, and that person is valuable, because what normal people are getting for normal cheapo construction prices is not good. It is not good. Now, here's the math. You don't need to remember this math. You don't need to memorize it. I just want you to know that it exists. What this says is that the U value, which by the way is the inverse in case you're a math-minded person, U value is the inverse of R value. So what you can do is figure out exactly how insulated each assembly in your house is, the walls and the ceiling and the floor, by taking the areas of those things and the insulated values of them and adding them up in a certain way and then dividing it by the total area. So what this means is that if you have a 99% perfect insulation job, it means that it actually does 66% of what you paid for. That's an exponential or a logarithmic relationship with your money. So you want to make sure that you always pay for 100% perfect. And if you're a contractor, listen to me say this, you tell your clients the same thing. Hey, I don't care if you hire my company, but I want you to know that you need to demand 100% perfection from whoever you work with. And they're probably going to have to come back to you because nobody's willing to do that.
Yeah.
So here's what energy modeling can do. Now, energy modeling means that we put the house, in this case the Tiny Lab, into a computer. And it looks like this, the software that we use. So we can put in the square footage and the volume, etc. We can do all this kind of analysis on the slab floors and the frame floors and the band joists and the above-grade walls, the windows, the doors, the ceilings, the mechanical equipment, the blower door test gets in here as well. And you can do all of this really cool analysis over here on how much we're going to use heating and cooling wise and how much all of this is going to cost. So we're going to go through all of these numbers here for you so that you can see exactly how this works. Now, this is what the energy model does. It is not about dialing in exactly how much all this is going to cost. It's about pinpointing what is the biggest weakness. As you can see in this graph down here, the above grade walls are my biggest problem in winter, and the windows are the biggest problem in summer, as well as the internal gains. The internal gains means like the refrigerator pumps out a lot of heat, the people inside pump out a lot of heat, all that stuff, right? So we're going to find out, where are we hurting and what can we do about it? So now we can experiment with some improvements. And I'm going to show you what experiments Grace and I ran on this thing. And we can run a cost-benefit analysis and start to prioritize what we are willing to spend money on so that we're not wasting a bunch of money on things that are not actually making a difference.
And just to kind of come back and bring it back to the logic, especially if you're not familiar with building science and not really familiar with these numbers, when you go to a doctor and you go and you get your blood tested, right? These labs come back with all these numbers, and your doctor is the one who walks you through and helps you understand, yeah, you're healthy. Your blood sugar is in a great place. Your iron is in a good place. You know, your vitamin D is a little low. You might want to start thinking about supplementing it. It's the same thing about a house. A house is a system just like your body. And so you don't have to have a degree in knowing all these numbers, but you do need to hire someone who is an expert in it. And so that's what we do.
Yeah. So the performance impact of different experiments. I want to just show you this real quick. Now, this is annual. This is how much it's going to make a difference yearly. If we do 2x4 walls with an R15 EcoBat, and that's a little bit extra R value. It's a specially engineered thing, just because I like doing as much as possible within reason. Within that 2x4 wall, that'll cost us $25 a year in heat and $40 a year in cooling. Based on the default values. Now again, this is not about exactly how much it's going to cost. This is about comparing that to this. Now I've got 2x4 walls, and I'm going to install R15 of open cell spray foam in the walls. How much is that going to save me? Well, it's not going to save me anything because open cell spray foam is exactly the same insulation value as batt insulation of a fibrous type, meaning fiberglass. Now, I can also experiment with 2x4 walls with an R25 in it, which is closed cell spray foam. That's what a lot of people will opt for in a tiny house because they think that it's going to make a big difference in their performance. However, as you can see here, we're going to save $3 a year in heat and $0 a year in cool.
And why is that?
Why is that? That is because all of the factors, the house is a system. So all of the things that are going into the house are having an impact on this, and just insulating the walls a little better, or even just one wall, which a lot of my clients will be like, well, what if we insulate that wall over there a little bit better? Or just the ceiling, or just that floor. It really makes much less difference than you think because the whole thing is a system. So remember that you can use any insulation material you want. You can use closed cell spray foam, and that is maybe what you choose to do because, remember, a lot of people use it for two steps. It is the air sealing and the insulation at the same time. I like a little bit more care and cost effectiveness and material effectiveness by just air sealing where the gaps are and then insulating with something that does a really good job. But as long as it doesn't look like any of these pictures, you're good. And these, again, are infrared images of these three things. So insulation will be defeated if it's not installed well. That's why if you see a billboard that advertises professional quality, do-it-yourself prices, if you're not paying for professional do-it-yourself prices, don't do it. So this is the way that good insulation does look. When it's installed well and uniformly, it's going to look exactly like this. You'll notice that the corners are dark, and dark, by the way, in these images is colder. You can see the scale over here on the right in the white. Dark colors are cold, light colors are warm, and in this case, we've got a summer day where the sun is beaming down on these two walls and ceilings, right? So that's good. Now, the energy model shows us a couple things about the HERS index. The HERS rating on this house, the way that we've described it with the 2x4 walls and the 2x6 ceiling and floor with batt insulation, is a HERS 68. If we go with 2-pound spray foam in the walls, we get down to a HERS 66. And if we go with also high-density spray foam or rigid foam in the floor and in the ceiling, we go down to a 64. That's saving us 4%. And this is in very, very broad terms. This is not mathematically exactly accurate what I'm talking about. But you can see that this does not make a huge difference. I'm not getting down to like a 50. A 0 on the HERS index, which you can see over here on the left, would be a zero energy home. So I'm already building a home, even at a 68, that's 32% better than a code-built home that is kind of a standard home from the 2004 International Residential Code. You don't need to know that. Don't worry about it. Here's what is the rubber meets the road. As described, this house is going to cost us $339 a year. With the upgrade in the walls to closed cell foam, we would spend $7 less per year. And with the R38 floor and ceiling, which is also the high density in the floor and ceiling, we'd save another $4 on top of that. So in all of these cases, remember, we're paying service fees for our electrical hookup, possibly, for our propane tank. Every time we go, we have to, pay a certain amount to just change it out. So all of that stuff is included in this. And remember that even if you don't have service fees, that amount is changing very, very little. So as I see this now, I am not going to invest twice as much money in spray foam as I would in batt, because I have done the analysis on exactly how it's going to perform.
And for a lot of us, one of the big reasons that we're going into tiny homes is not just to simplify our lives, but it's also to save money. And so bringing that approach to it, because we want to use our money on other things, frankly, like traveling and, buying nice camera equipment because I'm a filmmaker, things like that.
Yeah, exactly. So the third target, which is what we're about to wrap up on, is that my target is no liquid water comes in the house, right? That is not allowed. So I don't want any rain coming in the house. Now, the first thing that we want to remember from the first episode of this series is that we don't have roof eaves on this house. Damn it. So we wanted to hit all 8.5 feet of our possible width, and we didn't want to take up any of that with this roof that's sticking out. And at the front and the back, I don't want the wind ripping it off, which we talked about again with the aerodynamics in the first time. So what we are going to use is ice and water shield, which is an applied sticky membrane that's going to make sure it's essentially a rubberized kind of a thing, and we're going to use it in very specific places, and we're going to get into that down the line. You'll see that in the installation videos this winter. We're also going to have a rain screen for back venting the cladding, and the cladding, as you can see here, is this kind of like lapped siding deal. We don't know exactly what the cladding is going to be yet. You'll see that when we build it, but the rain screen is behind that, and you can find out a lot more about this online. And lastly, we're going to have a smart membrane. The smart membrane is really interesting. I want to make sure that you understand this. So it is not a vapor barrier. There's a very specific thing that's a vapor barrier, and that's something that stops water vapor. If you stop water vapor, it is a lot like a teenager. It will just try to piss you off now. So, don't make water vapor mad or stop it from doing what it wants to do. So it is not a sheet of plastic. What it is a material that has a very specific vapor permeance or vapor resistance. It means it slows it down or allows it through in certain measures. Now, what's smart about this is that it is variable. When the weather changes, it will change how it treats water vapor based on whether it's in the inside or the outside of the house. And this is what makes it genius. Now, this happens to come from Europe. We're going to be getting ours from 475 High Building Performance Supply out of the East Coast. And they have to ship it over here from Europe because they've got all the best stuff. That's, by the way, a picture of us in Switzerland looking at this stuff installed inside of a house. So here's how you prove that you control the water. Number one, you don't have water stains on the inside. And number two, even if you can't see water stains, you might be able to see it with an infrared camera. So the tips that we have for you are, number one, make sure that you have enough of an enclosure, meaning enough of an air sealing barrier, enough insulation, and enough flashing to ensure that you will control what's going on, meaning that you know what's going to happen, enough to be cost effective, and enough to be future-proof. If you can hit those first two things, go ahead and make your house so good that in 10 years, if you sell it, or 20 years if you sell it, it will meet the current codes in the future. Isn't that awesome? So the last thing is the energy modeling. We found very valuable for this, and we're going to get even more into this when we get into the load calculations, which are next week's webinar. So please do tune in for that. So I hope that you enjoyed today. We're going to go ahead and get into some questions here. So BJ says, I want to know about proper sealing below the trailer, insulation, and adding radiant flooring. I will be using solar plus a wetback system in winter. That's a great question. So what's really interesting, BJ, if you tune in next week on the HVAC side of things, we're going to be going over exactly how much heating and cooling this house needs. So I'm assuming, BJ, you're talking about a tiny house that you're building for yourself since you mentioned a trailer. The ceiling below the trailer is really important. You're going to want to make sure that it's shielded from water. So that is why our trailer builders, which is Tiny Home Builders out of Atlanta, are going to be sheathing the underside of the trailer assembly with roofing material, essentially. Two things. Number one, it's going to block water from getting up inside there. And number two, if water does get up inside, it's got those standing seams that it's going to kind of fall down into and be able to drain out. Especially when we're moving, obviously, that's not a concern of it staying in there. So I'd say definitely stay tuned for that next week, BJ, because we're definitely going to talk about that. BJ also says, what about ceiling insulation and the need to vent to reduce condensation? Great question, again. And I am going to open up the chat just a minute. I want to get to some of these. So the ceiling insulation, and I'm sorry that we spent so much time today going over the walls and kind of the dialing in of that, but the ceiling insulation we're going with is R21 2x6. And I may even decide to dial that back to 2x4s. We're still kind of going back and forth about this because of weight, dropping that center of gravity that we were talking about last week. So the ceiling insulation that we're going with is an R21 bat of EcoBat, and that is between 2x6s at 24 inches on center. And that actually is going to perform fantastically. That's all of the stuff that was in the calculations today. The need to vent, this is really, really important, and I want everybody to make sure that they understand this. The reason that you vent any cavity is not to let heat out. So an attic doesn't have ventilation to get heat out. That's why, if you want to watch my video from this past week from the Building Forensics Mastermind webinar, attic fans are totally ridiculous. So please don't install those. But you're not installing it to cool it down. You're installing it to dry it out. And the reason that it's wet inside of any cavity is because hot, moist air is getting into that cavity from the house generally. So if you just stop air from getting into the cavity from the house, then you have solved the problem and you do not need to ventilate. So we are not going to have ventilation for our ceiling cavity because I will have proved with the blower door while we're building it that there is no possibility of air getting from my house into my ceiling cavity. And if the ceiling cavity is the same relative humidity and temperature as outside, that actually is not a problem because it is outside. That's what I want. So that's how we deal with that, BJ. I hope that answered your question. David says, need to run to an appointment. Look forward to seeing your recording at the website. Catch you next week. Rock on. All right. Leslie says, aerogel, ... starting to be used. Very expensive. Yes, Leslie, you are totally correct. Aerogel, if you guys don't know, is a NASA-developed insulation that is translucent. Grace and I were talking about building a house inside of a house when we were thinking about living in Chicago long term because we're both from the South. And we were going to sheathe the entire ceiling in aerogel, which would be insanely expensive. But it's the most insulating material on Earth, which is nice, but it's also, yes, incredibly expensive. The short answer is, I hope that you heard a lot of what we were talking about today. You do not need aerogel in a tiny house or in a normal house because it's going to deliver an overperformance that is miles past anything else that you could possibly do in the house, and you will not get credit for that in the performance of the house. So aerogel is overkill on everything except a space vehicle at this point. And if you have some special engineering application that you want to use that for, or an engineer would want to use it for, they would make sure to do an energy model first before they spend all that dough on something that absolutely is not going to help them. So I hope that answered your question.
In Florida, Joe Shearer is down there, and he says our attics are over 125 degrees. Attic fans can lower them 10 to 20 degrees. Are they always bad?
That is an excellent question. And the answer to that question, and I understand that I say things that are going against what a lot of people have heard, but it's only because I have actual scientific proof of what's going on. And you'll find a lot of this going on out in cyberspace as well. You can look this up. Attic fans are going to cool the attic down from, let's see what Joe said, so 125 degrees in Florida. Here is the thing. The attic is not a part of your conditioned space. It's not a part of your house, effectively. You consider it a shed that happens to be attached to your house. In theory, let's just imagine for a moment that your attic is actually made out of like all metal for just a second. It could be 500 degrees in your attic, and if your house is air sealed and insulated away from that effectively enough, it doesn't matter. And that's what I would tell all of my clients. So your attic can be as hot as it wants to be, and it doesn't matter. In fact, the roofing manufacturers are a big reason why we are so obsessed with this attic ventilation. They used to void their warranty if you put insulation up against the backside of the roof. They have since redacted that, and they actually don't void the warranty anymore for that. So that is the big deal. Also, the attic fans are not just not helpful in making you more comfortable, because remember, the main problem is the air sealing between the house and the attic is not very good, and the insulation probably isn't thick enough. It also is going to, if there is air leakage between the house and the attic, it's going to suck on the house. And if you have what's called atmospheric drafting appliances in your house, like a water heater or a furnace that's a little bit older, that attic fan could potentially cause a very dangerous situation in your house because all things are connected. So that is the big thing, is if an attic is connected to the house, the least of your worries is how hot it is in the attic.
Yeah, literally, we just dealt with this last week, 2 weeks ago, where we had a client who every morning they would wake up and they'd smell their fireplace, literally, like the stench of their fireplace. And they hadn't made a fire. It's the summer, so what's going on? And it was those solar fans that never really turn off unless the sun goes down, and pulling that fragrance up.
Yep. So Leslie is asking, I have heard that bats, meaning bat insulation, which are like blankets of insulation, shrink and sag, so leaves air pockets. That is actually not true if it's installed properly. So the big deal about all of this is, remember that if you design it and you say, I expect this to be perfect, and then during installation you go and you check it visually and you make sure that there are no gaps and cracks, when you put that facing on that, whether it's drywall or plywood in a tiny house or whatever, on it, there is no way for it to sag because it's tight in there. So Leslie, I think that where you probably heard that from is a marketing firm that's trying to get you to not buy a bat, right? They want you to buy something else. And this is why it's so noisy in the construction space right now, is because everybody wants you to buy their stuff. And it's just, the truth is that stuff is only as good as the way it's installed. And that's why the companies that are really making a big deal about, hey, make sure that this gets installed the right way, we will come and check it for you as included in the price or whatever, those are the ones you really want to pay attention to. And by the way, I see that all the time. That's not anecdotal. That is from my work over the last 7 years in Chicago. Joe says, our ductwork and HVAC equipment is in there. That is an even bigger deal. That's a great question, Joe. So if your ductwork and HVAC is in the attic, That is exactly the kind of thing where now this becomes an even bigger problem with the attic fans, which is what we were just dealing with. So if the attic fan depressurizes the attic, and the ones that I just measured last week, which had a ton of ventilation to outside in addition to these attic fans, were depressurized by 4 pascals. If you've got water heaters, God forbid, which I've seen, or natural draft or induced draft furnaces in the attic, it is entirely possible that an attic fan could actually affect the performance of those pieces of HVAC equipment. And also, since you've got the ductwork up there, that is a big air sealing opportunity as well. So I hope that.
So yeah, and the performance of the HVAC and the water heater, God forbid, we're also talking about backdrafting. We're talking about combustion, and we have seen ashes and fire that has licked the outside of its equipment because of this backdrafting. So, I mean, nobody wants that situation happening in their attic, because then you've got a very, very dangerous situation of potentially having your house burned down, which would defeat all of it.
Yeah, that sucks. Wonderful. Thank you very much, Joe. So thank you guys all very much for spending time with us tonight. I hope that you check out the rest of the series, and also if you want to revisit this or the last webinar, both of them are going to be recorded and on our YouTube channel. So thanks very much. Hope everybody has a great night. Tune in next time.